Astronomy compels the soul to look upwards and leads us from this world to another. Plato spoke those words 2,400 years ago. Astronomy leads us from one world to another. So which world should we go to next? Young people today are clamoring for us to go to Mars. It seems that's all you hear today. Mars, Mars, Mars. This is understandable. Each generation wants to extend the frontier, push back the boundaries. We are anxious to do what has never been done before. And of all those places humans have never set foot, Mars appears to be the easiest to reach. What Mars has going for it is 2 moons, a thin atmosphere, and thousands of years of our wonder. But is the red planet really the right answer to the question, where should we go next? Let's examine a few alternative destinations. Mercury is the planet nearest the Sun, and as such has loads of available solar energy. Mercury is also nearly tidally locked, so it has a hot side and a cold side. Mercury experiences the most extreme temperature variation of any planet, from a high of almost 800 degrees to a low of nearly 300 degrees below zero, with every temperature in between represented somewhere on its surface. Water ice lies at the bottom of craters near Mercury's poles, permanently shaded. We could establish a base in one of those craters, or a mobile base near the terminator. The line between light and dark would also have an acceptable temperature. Now, what would we do with boatloads of solar energy harvested on Mercury? One possibility would be to use that energy to heat Mars. Because Mars is much farther from the Sun than Earth, it is much colder, and one of the things you need to do to terraform it is heat it up. There would be vast arrays of solar panels either on the surface of Mercury or orbiting around Mercury, funneling energy into one or more giant lasers beamed to Mars. Now, a laser beam doesn't remain perfectly collimated, that is, perfectly straight and parallel. It eventually begins to spread, and over the distance between Mercury and Mars, we could focus it so that it spread out just enough to cover the diameter of Mars. Next out is Venus, Earth's twin. The surface temperature on Venus is over 800 degrees, so it seems insane to talk about going to Venus. Venus is experiencing a runaway greenhouse effect, which makes it the perfect laboratory. A living laboratory where we can study how to deal with a runaway greenhouse effect. This is a concern right here, right now on Earth. It should be a high priority for us. Of course, we would not, at least at first, put a base on the surface of Venus. That's crazy talk. What we do is have a floating base, like a Goodyear blimp, high in the atmosphere of Venus, where it is much cooler. This is an artist's rendition of HAVOC, a proposed NASA mission. Now, once we learn how to deal with a runaway greenhouse effect and begin implementing aspects of a solution there on Venus, what we'd actually be doing is terraforming Venus. Once Venus is terraformed, we can move on to its surface. And the wonderful thing about Venus is, it's about the same size as Earth. When you stand on Venus, you will experience about the same gravity as you experience here. So you can travel back and forth between Venus and Earth with no ill effects. Contrast this with Mars. If you move to Mars and spend any significant period of time there, you will find it quite difficult to return to Earth. For most people, no matter where in space we go, we want to go there and back again. But before we attempt to cross the gulf separating us from the other planets, perhaps it would be wise to return to the moon. We need to recapture the technical know-how we had during the Apollo missions and extend and refine those abilities before we venture further afield. Our moon, airless, massive, and nearby, is a good place to hone our spacefaring techniques. In addition, there's an economic incentive, which is lacking in some of these other destinations. An economic incentive as in profit to be made. Our moon is unique in the solar system in that it has accumulated on its surface something called helium-3. Helium-3 is an isotope of helium. Particles of helium-3 are expelled from the sun continuously in the solar wind. These particles hit every planet and moon, but if the planet has an atmosphere, the helium-3 doesn't reach the surface. If the planet has a magnetic field, the helium-3 doesn't reach the surface. Mercury doesn't have an atmosphere, but it does have a weak magnetic field. Venus obviously has a very, very thick atmosphere. So where in our solar system can you find helium-3? It's in the top 6 feet of our moon. So what good is helium-3? It is very important for fusion technology. If we had a good source of helium-3, we could already have fusion reactors generating electricity for us at a price nearly too cheap to meter. There's an economic incentive to return to the moon, as well as many learning opportunities. Now, once you've mined the helium-3 off the surface of the moon, you'll need some way to get it into orbit around the moon and eventually back to Earth. And one way to do that is something called a mass driver. Remember, there's no atmosphere on the moon. So once you've accelerated something up to speed, it will keep going, only affected by gravity and not affected by the friction of an atmosphere. You just need to get it up to orbital velocity. A mass driver, which you can think of as a rail gun or an electromagnetic catapult, uses sequenced electromagnetic fields to accelerate a payload. The presence of helium-3 on the surface of the moon gives us an economic incentive to advance mass driver technology. Any one of these projects, a mobile base on the terminator of Mercury, a floating laboratory in the clouds of Venus, helium-3 harvesting on the surface of the moon, or a colony on Mars, will be very expensive. But our financial resources may only be sufficient to afford one of them, at least at first. So, which one do we choose to go to next? None of them. Instead, we should use that money to build the space travel infrastructure that will eventually enable us to do all of them. Each one is very expensive. And why are they so expensive? Because travel around the solar system is expensive in terms of time and energy. What we need is a cheaper way to go, a faster, cheaper way to go. And fortunately, there are possibilities out our current technology, using rockets to travel around the solar system, is slow, costly, polluting, and wasteful of energy. Rockets use reaction mass, which they're throwing out the back end to push the payload forward. If you want to add more payload, you have to put in more fuel. But that fuel has to be accelerated too. So you have to add extra fuel to accelerate the fuel that you just put in. It's a diminishing returns scenario. Consider the energy needed for a round trip between Earth and Mars. If you start in orbit around Earth and proceed to orbit around Mars and return to orbit around Earth, from a physics point of view, you haven't changed your gravitational potential energy status at all. And there's no reason why you should have used any energy at all. Think about it like this. When you're on a bicycle on top of a hill, you can coast down to the bottom of the hill and up to the top of the next hill. But if you're riding a rocket, you're going to be burning fuel the whole way, half to accelerate and half to decelerate. We need space travel that is not so wasteful, costly, and time-consuming. And there are some options we can explore. Solar sails would allow us to slowly change orbits without using any fuel. Space elevators and skyhooks offer ways to get on and off the surfaces of planets and moons. But what I want to focus on is the mass driver we were talking about back on the moon. Think about for a moment being in an electric car. When you accelerate in that electric car, it pulls energy out of the battery. Then when you get to a stoplight, you hit the brakes. And what happens when you hit the brakes? It feeds energy back into the battery. It's called regenerative braking. It recaptures as much of that energy of momentum as it can. And that's what we need. We need a mass driver that we can use to launch ships out of Earth orbit toward Mercury, Mars, Venus, wherever we want to go. And at each destination, we need a reverse mass driver that catches it and recaptures as much of that energy as it can. I imagine a solar circuit, a web of electromagnetic launch and capture points all around the solar system, where the energy from an inbound ship is captured and used to launch the next ship out. This would greatly reduce the cost and the waste, and also allow us to achieve incredible speeds, hastening our exploration of the solar system and beyond. There's a difference between what the laws of physics tell us is possible and what our current technology makes doable. When the race to put a man on the moon began, was it physically possible? Yes. Was it technologically possible? Not then. But we challenged ourselves and won the race, and in so doing made amazing technological advances. Everything I've suggested here today is physically possible and worth doing. Once again, we should accept the challenge as we face the question, where do we